In this lecture, we'll speak about social choice functions. The most famous impossibility results pertain to social welfare function, and in particular, the Arrow's impossibility theorem is widely known, and we have discussed that before. Now, it might be thought that the problem lies in the fact that social welfare functions require you to specify as an output of the process an entire ordering, and that might be highly constraining. But if you only needed to pick a winner, as does a social choice function, then you would escape these paradoxes. It turns out that the answer is no, but first we need to sort of redefine our criteria a little bit, because the notions of Pareto efficiency and independence of irrelevant alternatives just aren't well defined in the context of a social choice function, but we will see that there are closely related notions that are well defined. So let's first define weak Pareto efficiency. And we'll say that a social choice function C is weakly Pareto efficient if essentially it never elects a dominated outcome or candidate. So if there is a candidate O2 such that there is some other candidate O1 that is always preferred to O2 by every voter, then the weaker candidate O2 would never be elected. Seems like a reasonable criterion, and we'll call that weak Pareto efficiency. In place of independent of irrelevant alternatives, we'll have the notion of monotonicity. And informally, as is written here at the bottom, it says that if you have a winner, if we increase the support for that candidate, they would still remain a winner. So formally speaking, we'll say that the social choice function is monotonic if we take any candidate, O, and if it's the case for any preference profile, this one over here, if under this preference profile O is selected, then if we look at any other preference profile, if it has the property that for every agent and every other outcome O prime, if under the original preference O was preferred to O prime, it is also under the new preference. So that original winner O never lost support, maybe only gained support. Then under those conditions, it better be the case that under the new preference order, in which O only got more support, it would still be the social choice, the winner. Again, a reasonable property to require. The last notion of dictatorship, similar to what you see in social welfare, simply says that C is dictatorial if there's some agent whose top choice is always the social choice. This is the bad news. The Myerson-Satterthwaite theorem tells us that we can't have all three. So if a social choice function is Pareto efficient and monotonic, it must be dictatorial. And so, after all, social choice functions aren't more benign than social welfare functions, and we won't go through the proof, but the intuition is that in order to determine the relative ordering among candidates, we need to sort of probe it everywhere. And if we probe it enough, we'll get the entire social welfare function. And since the function, the social choice function, must be defined for all inputs, as we vary the inputs, we can find the total social welfare ordering. So in fact, we can use the social choice function to recover the social welfare function. That's the intuition behind the proof, and why social choice functions are as maybe counterintuitive or complicated as social welfare functions. Now, just to test our intuition again, let's consider an example, and let's take plurality, which perhaps on the face of it might contradict the Myerson-Satterthwaite theorem. Clearly, plurality is Pareto efficient. In other words, if everybody prefers some candidate to another candidate, that other weaker candidate will never be the choice. And it's not dictatorial, obviously. So the theorem says it cannot be monotonic. Intuitively, you might think it is monotonic, but here's a counterexample. So here are these 7 agents and their 3 preference profiles. The 3 of the agents prefer A to B to C, etc. And clearly then A would be the winner under plurality, because 3 agents would vote for A. Now, what happens if we go and we modify this preference to this preference? We simply make A's situation better. C was preferred to A originally, and now A is preferred to C, and all other preferences relative to A remain the same. So surely you would say A is doing as well as it would have done originally, and monotonicity would say that it should be the winner, but clearly in this case there are now 4 agents who are voting for B versus only 3 for A, so B would be the winner now. So plurality is not monotonic.
Okay, we've seen some results on the difficulties associated with aggregating preferences coherently, and what I want to do is talk a little bit about a setting where things are nicely behaved, and these are known as single-peaked preferences. And sometimes voters' preferences have nice properties, and a very prominent case of that is when candidates can actually be ordered from left to right. So we can think of leftmost candidates, rightmost candidates, and candidates can be nicely ordered. And in situations where people have a most preferred outcome or candidate on this spectrum, then candidates we're going to have nice properties in terms of having an existing Condorcet winner, having nicely defined voting schemes, and so forth. And so the idea here is people have a most preferred point, and they prefer candidates closest to that and don't prefer ones that are further away. Now, we can think of this in a political spectrum. You could also think of, how much tax would you like to have? Well, people might have an optimal tax rate and not like to have higher tax rates or lower tax rates, or what's the extent of some regulation. We can think of a series of different settings where we have a nice ordering over the alternatives, and people's preferences are going to have this property. So in particular, when we think about, so our set of outcomes, let's say our set of outcomes here is A, B, C, D, E, and we look at a person who has single peak preferences, we look at, say, the utility. So here, the utility, the payoff they get from a given alternative, and their most preferred alternative in this case is B. They get the highest. And then when we look at the other alternatives, in this case, C would be second highest, A would be third highest, then D, and then E is way down here. So their preferences would look like B, C, A, D, E in terms of a ranking. But what's important in terms of single-peakedness is that the further you move this way, the lower the preferences, the lower the utility is. So the voter always prefers something which is closer to B than something further away on the same side. And similarly, the more you move in this direction, the voter prefers the alternative B to A or anything further to the left of A. So that's what's known as a single-peaked preference. And the fact that you've got this nice ordering, and it can be ordered on a line with a most preferred alternative and things getting worse when you move away, that kind of preference means that you've got nice voting procedures and the existence of Condorcet winners. So let's have a peek at that. just to understand why things are going to be better behaved in this kind of world. So imagine we had 3 voters that have single peaked preferences, and we had our A, B, C, D, E. So we'll keep an odd number of voters to make sure we don't have to worry about ties. What's true then is if we look at the median most preferred outcome, that's going to be a Condorcet winner. So in this case, that's B. So B's most preferred by this middle person. So let's call this person 1, person 2, person 3. Person 3's most preferred alternative is D. Person 1's most preferred alternative is A. And let's verify that this outcome B is actually going to beat everything in a pairwise comparison. So suppose we compare B to C. Well, both persons 1 and 2 like B better than C. They also like it better than D and E, right? So given the fact that when we look at the median voters, all the voters to the left of the median are going to prefer the median's peak to any alternative which lies to the right, because going to the right, further to the right, is bad. And similarly, we're going to have a majority of people on the right preferring the median's alternative to anything that's to the left of the median's alternative, the median's most preferred alternative. So the median outcome here, is a Condorcet winner. Median meaning median peak here, right? So we look at the peak, we look at the median of the peaks, that's a Condorcet winner. And so we're going to have a well-defined alternative which is going to beat every other one. And this gives us a nice way of choosing an alternative. It's known as median voting, and it gives us an idea of why we always talk about median voters and so forth, because then we've got a majority that prefers that position to anything on the other side, and vice versa. We have a Condorcet winner. Moreover, this is going to have nice properties in terms of people misrepresenting their preferences, right? So could 2 improve by changing their ordering? No, their alternative is picked, right? B, their favorite ordering. Let's think about person A. How could you affect this by if you're median voting, we're picking the median of the 3 alternatives. So if we think about picking the median alternative of these 3 alternatives, then the only way that person 1 could affect the outcome would be to change the median. How could they change the median? They would have to announce a peak over here, C, D, or E. And all of those alternatives are worse than B. So there's by misrepresenting their preferences, this person 1 would actually do worse. So this is, and you can verify that that's also true for 3 or any individual. The only way you're going to be able to make a difference is to change the median, which means you have to flip to the other side, which is something you're generally not going to want to do. So nice thing about single peak preference worlds, median most preferred point is a Condorcet winner, and individuals are going to have incentives to be truthful and to announce their preferences in a truthful manner. In fact, it's going to be a dominant strategy if we ask people for their preferences to announce their truthful preference if we're using majority voting. Median voting in this case. So there are settings where a lot of the negative results of impossibilities of aggregating preferences are overturned. And those are going to be ones where we've got a lot of structure on the problem, and that structure of the problem means we have nice orderings and there's no voting cycles. So this kind of setting, there's no voting cycles. We don't have the difficulties that underlie some of the issues like Arrow's theorem and so forth. Once we go into this setting, we have a nicer set of preferences in terms of the restrictions that they satisfy, and that allows us to aggregate preferences in ways that are going to be nicely efficient, strategy-proof, having dominant strategies and so forth. So there are settings which are quite natural where things are going to work out more effectively than they do when we allow for all preference orderings over alternatives. Now, when that happens depends on the setting, and there can be situations where you don't have this nice left-right ordering. So it is a fairly restrictive setting, but one that at least captures a good number of applications.